Hey guys, so today we're going to be going over the last lesson of the first unit. You once again need to apply your knowledge of the shapes of different molecules and what their polarity will be in order to figure out what type of molecular forces they have. So today's lesson is all about molecular forces. So in this lesson on molecular forces, we're going to go over the difference between intermolecular forces and intramolecular forces, which we did already touch on briefly earlier in this unit. Then we're going to go over the different types of intramolecular and intermolecular forces, and you do need to be able to identify what type of forces are present in a molecule given nothing but its name or formula, which means that you will, once again, need to know the shapes of these different molecules. And then you also need to know the effects of these intermolecular forces on the properties of covalent or molecular substances. So, like we said, there's two main categories of forces. There's the intramolecular forces and the intermolecular forces. Intramolecular forces occur within a molecule between the different atoms of that molecule, but it's all within the molecule. So ionic bonds and covalent bonds are intramolecular forces, and they are very, very strong. Intermolecular forces happen between two completely different molecules, and they only happen in covalent or molecular substances, and compared to the intramolecular forces, they're quite weak. Okay, so the intermolecular forces, those are just the normal ionic and covalent bonds that you're familiar with. So ionic bonds, where you have that force of attraction between two oppositely charged ions. So you always have a metal, which is positive, a non-metal, which is negative. They become ions and then attract each other. That is your ionic bond. And this crystal lattice structure is what forms here, where we have all of these ionic bonds between oppositely charged particles. Then we have our covalent bonds, which are when you have two nonmetals bond together by sharing electrons. And as we've already talked about, that can be polar or non-polar depending on if the electrons are shared evenly or not. But regardless, that covalent bond is an intramolecular force. It's holding that molecule together. The intermolecular forces, again, are a little different. They're not inside those molecules. They are between two different, completely distinct molecules. And there are three types of intermolecular force. From weakest to strongest here, we have the London force, the dipole-dipole force, and the hydrogen bonding. There also used to be a force called van der Waals force, so you might still see that in like a textbook or online or something. But now scientists believe that it's actually just a combination of those three intermolecular forces and that it's not a distinct force. So these are the only three forces that we're going to go over. The London force is the weakest type of intermolecular force. And again, remember, all of these intermolecular forces are way weaker than the intramolecular forces of the ionic and covalent bonds. But this is the weakest of the weak. It results essentially just from the random movement or vibration of electrons. So even in a completely non-polar molecule, you might have an electron that just like hops over to like one side of the molecule for a second. Sorry, the bell's ringing. So if that electron just kind of like hops over to the other side of the molecule for a second, then that side becomes slightly negative, but just for a second, and then the electron will move on again because electrons are in constant motion. So it'll create these little very, very temporary, momentary dipoles where you have a slightly negative and a slightly positive end, but it happens for a split second and then it's gone again as those electrons are just randomly moving. But during those brief moments of that dipole, the positive dipole of one molecule can attract the negative dipole of another molecule. So you have this brief moment of attraction and then it's gone again. And then you might have another brief moment of attraction and it's gone again, okay? The more electrons in a molecule, the stronger the London forces will be because you have more of that random movement of electrons. And also the closer the molecules are, the stronger that force will be. Then we have the dipole-dipole, which is a force of attraction between polar substances. Also, by the way, London forces technically occurs in all molecular compounds, so all covalently bonded compounds. However, it's pretty much negligible in everything except the nonpolar molecules. So nonpolar molecules, this is the only intermolecular force that they will have, is the London force. Other molecules will also have London forces, but they're pretty much like overpowered by whatever the other intermolecular force is. So London forces are really only important when it comes to our non-polar molecular substances. Okay, the dipole-dipole, that can only happen if, sorry, the bell is ringing again. The dipole-dipole attraction can only happen if both molecules are polar. And this is essentially what happens is you have the slightly negative end of one molecule being attracted to the slightly positive end of another molecule. So here we have a hydrochloric acid molecule. So this is an intramolecular bond right here connecting the H and the Cl. This solid line over here, also an intramolecular bond. Those are both covalent bonds. And this dotted line is representing the intermolecular force, the dipole-dipole, where slightly negative end of one and slightly positive end of the other molecule attract one another. Again, can only happen between molecules that are polar. And the more polar the molecules are, the stronger the dipole-dipole. And then the last type of intermolecular force, which is the strongest of the intermolecular forces, though still fairly weak, is essentially just an extreme dipole-dipole. It's still just a force of attraction between a slightly negative pole of one molecule and a slightly positive pole of a different molecule. However, it's a really, really strong dipole-dipole, and it only happens in molecules where you have a hydrogen bonded to either a nitrogen, an oxygen, or a fluorine. NOF. So if a hydrogen is bonded to NO or F, and in this case, the hydrogen is bonded to an O in both of these molecules. So as soon as we have that, you can then have a hydrogen bond form between the poles of those different molecules instead of a dipole-dipole. And the only reason that happens is because the difference in electronegativity between the hydrogen and the NO or F is just like a huge difference in electronegativity, which means these are super polar molecules. So they essentially end up with like a super strong version of the dipole-dipole, which is the hydrogen bond. And that happens because out of all of our non-metals, hydrogen has the lowest electronegativity. NO and F have the highest electronegativities. So that big difference in electronegativity makes them super duper polar. So this is just kind of a flow chart showing you the difference between all these different things. So we have our intramolecular forces and our intermolecular forces. Intramolecular are within the molecule, they hold the molecule together. They are our ionic and covalent bonds, and they are both very, very strong. The intermolecular forces are between separate molecules. They're all fairly weak, but the London forces is the weakest. The hydrogen is the strongest of those three. Okay, the effects of intermolecular forces. So they can change things like boiling points. The stronger the intermolecular force, the higher the boiling point of that substance. So for example, when we just went over like dipole-dipole forces, the example here is hydrochloric acid. The hydrogen bonding example is water. Because hydrogen bonding is a stronger intermolecular force than the dipole-dipole, water is going to have a higher boiling point than hydrochloric acid, which would have a higher boiling point than something that's non-polar and would have only London forces, like oxygen gas or nitrogen gas or chlorine. So yeah, that's because when a substance is boiled, the molecules have to spread out, and the weaker the forces holding the molecules together are, the easier it is to get them to spread out. So if all you have between two molecules is a London force, it's not going to be hard to get them to spread out and become gases and fly off. If you have a hydrogen bond holding the molecules together, it's harder to get them to spread out. You have to heat them up more and more, get them moving more and more in order to finally break that hydrogen bond and get these molecules to turn into gases and fly away. So yeah, it is also important when it comes to, So when it comes to intermolecular forces and boiling points, obviously only covalently bonded molecules have intermolecular forces. We already talked about that. And so when you boil a covalent substance, you break the intermolecular forces. You don't break the covalent bonds when you boil a covalent substance. So like when you boil water, for instance, if I go back to this example, when I boil water, I break this intermolecular bond, this hydrogen bond. I don't touch these bonds, these covalent bonds, when I'm boiling water. And that's true for all covalent substances. However, if you need to boil an ionic substance, you need to actually break the ionic bond. So it's much harder to break an ionic bond than it is to break these intermolecular forces. And that's why ionic substances have much higher boiling points than covalent substances. Because with ionic compounds, if you boil them, you have to break the intramolecular bond, the ionic bond. If you're boiling covalent substances, you don't touch that intramolecular bond, you only break the intermolecular bonds or forces, which is much easier. What else? Hydrogen bonding also allows for the formation of protein chains. It's what allows your DNA to be held together and then split apart to replicate and then attached again. So DNA replication wouldn't work without hydrogen bonding. It's also the reason, oh my gosh, someone keeps ringing the doorbell. Hydrogen bonding is also the reason that water expands when it freezes, because those really rigid hydrogen bonds actually hold the water molecules really far apart. Most things shrink when they get colder and expand when they heat, and water is the only thing that it expands when it heats. It also expands when it freezes. And that's all because of the hydrogen bonds. So that's the reason that ice floats. Without that, everything would die in a lake every winter. And then surface tension, adhesion, which is molecules, oh my gosh. Adhesion, which is molecules sticking to the walls of things. I actually have these like listed backwards. Adhesion is molecules sticking to the walls of things. Cohesion is when they stick together. Capillary action, which is the ability of water to go up tubes. All of those are because of hydrogen bonding, and trees wouldn't be able to get water up them if it wasn't for that. So anyway, intermolecular forces are really important. That's kind of the point that I was trying to make there. Let's go over some examples of how you would have to identify intermolecular forces. Okay, so let's just quickly go over some molecules where we're identifying the intermolecular forces that would exist between different molecules of this substance. So the first is iodine, and with all of these examples, I've given you the name. I would recommend you start by writing out the formula. So iodine is I, and because it is a Hofbrinkel molecule, it's one of our diatomic molecules, we have to put a little 2 beside it. Now, if I draw out my iodine, it's going to look like this. So it's linear, but since both of these molecules are the same, neither one is slightly positive and slightly negative. This would be an equal sharing of electrons in this bond because neither of these iodines has a higher electronegativity than the other. And so this would be completely nonpolar. And because of that, its only intermolecular force would be a London force. Okay, so we start with the formula, we draw it out. Based on its shape, we figure out if it's nonpolar or not. And if it's nonpolar, it's definitely a London force. Next up, we have ammonia, which is NH3. So if I draw this out, and again, do your sausage diagrams if you need to, if it helps you, absolutely do that. I would actually recommend doing it, but you don't have to if you don't need to. Ammonia would look like this. This is a trigonal pyramidal, and because of these unpaired electrons around my central atom, I know that this is definitely polar. Essentially, in each of these bonds, I would have the electrons being pulled towards the nitrogen, which would make that slightly negative. My other poles are slightly positive. So yeah, it is polar. Even if you don't draw these arrows and these slightly negative and slightly positive signs, those two electrons around the central atom tell you it's polar. When it's polar, you then need to check, is it hydrogen bonding or just a dipole-dipole? Now, because I have an N bonded to an H, that tells me that this is actually hydrogen bonding. Okay, if I have an H bonded to an N, O, or F, all of those would be hydrogen bonding. In this case, I've got the N bonded to an H. So that's what makes this hydrogen bonding. Okay, next up we have methane, which is CH4. So if you draw that out, it's going to be a nice tetrahedral shape. Because my central atom has no unbonded electrons and everything around the outside is the same, this is going to be nonpolar. So once again, the only thing it can be is London forces. By the way, this ammonia would also have London forces, but it's not going to be the main intermolecular bond, but it would also have a little bit of London too. All molecular substances have a little bit of London. It's just negligible in polar substances. Okay, last up we have sulfur dioxide. So SO2, because di means two. Draw this one out, and this one is a little bit trickier, so I'm going to show you how to actually sausage this one. The reason I didn't bother sausaging the other ones was because like H's only have one bonding site, so does I. But here we're dealing with things with more than one bonding site, so I'll draw it out for you. So my sulfur goes in the middle because I only have one of it and I have two oxygens. I'm going to make sure that all of my lone electrons on the sulfur are bonded with something, so I've bonded them to that oxygen. Now I have this oxygen that needs two bonding sites, so I will take these two electrons and separate them into two different bonding sites like so. So I end up with a sulfur double bonded to two different oxygens. It is important that you do not draw this like so. Do not draw it so that it looks linear. Remember, these extra electrons on the top are going to push these bonds downwards so that it's not linear, it's bent. These electrons also, the unbonded electrons on our central atom, tell us that this is polar. Once it's polar, we're going to see if it's possible for hydrogen bonding to be present, but because we don't have a hydrogen bonded to an NO or F, it's not going to be hydrogen bonding, it's just going to be the normal dipole-dipole. Okay, and that's it. That is how you determine what the main type of intermolecular force is present. Other than that, just pay attention to wording in questions, like if I say, if we're talking about ammonia, for example, and I say, what is the main force between ammonia molecules? That would be the hydrogen bonding. But if I say, what is the main force within ammonia molecules? That's actually just the covalent bond. Okay, so also watch out for that wording, the difference between within a molecule and between molecules. Okay, that's it for today.